Welcome to Fundamentals of Artificial Intelligence. Today we will review knowledge representation and reasoning, particularly to motivate the introduction of formal logics as a knowledge representation formalism for artificial intelligence. Knowledge representation and reasoning forms the backbone of any intelligent behavior through computational means. In fact, human intelligence is also driven through knowledge. Most complex and mysterious phenomena is the intelligence that humans exhibit. But the striking aspect of intelligent behavior is that it is clearly conditioned by knowledge. Decisions for a wide range of activities are based on what we know or believe. Intelligent behavior that we arrive through computational means, knowledge representation and reasoning, allows an agent to decide what to do based on what it knows. What is important for such a system to be in place is to have structures for representing the knowledge and then certain computational processes for reasoning with those structures. This is what we will look at today and try to motivate how formal logic forms a very interesting choice to be taken up for representation of knowledge in AI. But then what is knowledge? In order to understand knowledge, we start with the basic definition of what we mean by data. Data is primitive verifiable facts of any representation, and data reflects the current world. Data is often voluminous and it is frequently changing. As you process data, you get information. So any interpreted data is information. Knowledge is one step ahead of this. It's about the relation among sets of data that is very often used for further information deduction. Knowledge is, unlike data, general, and knowledge contains information about behavior of abstract models of the world. Now, from the very beginning of AI, there has been two approaches to look at artificial intelligence. One believed that developing an intelligent system was to be based on rules and knowledge, and any intelligent behavior is actually manipulation of symbols. This approach to AI is called the symbolic AI. So the traditional symbolic approach was introduced by Newell and Simon in 1976 and describes AI as the development of models using symbolic manipulation. Then there is the other approach to AI, which is called connectionist AI. The connectionist AI strives to build a computational system inspired by the intricacies of the human brain. We will not go into the details of whether symbolic AI or connectionist AI is going to win the race of creating an intelligent system, but then we like to point out that there is a realization that there needs to be some convergence of both the approaches to really have an interesting intelligent system in place. We will neither talk of that convergence here and only focus our attention on symbolic AI. So knowledge representation that's based on the knowledge representation hypothesis is an essential problem of symbolic based artificial intelligence. The knowledge representation hypothesis put forward by Brian Smith in 1982 states that any mechanical embodied intelligent process will comprise of structural ingredients that will represent somehow the propositional account of knowledge, and independently of such a formal semantics will play formal and causal role in performing the behavior that manifests the knowledge. The symbol system hypothesis is a position in the philosophy of AI which was put forward by Alan Newell and Herbert Simon The physical symbol system hypothesis states that the necessary and sufficient means for general intelligent action is a physical symbol system. Now, there are two things to observe from this statement. One, that human thinking is a kind of symbol manipulation, because the symbol system is necessary for intelligence. That's what they have stated. Therefore, we could say that human thinking is a kind of symbol manipulation. And the other is that because a symbol system is sufficient for intelligence, we could have machines that can be intelligent. According to the symbol system hypothesis, knowledge may be represented as symbol structures. Essentially, we would have complex data structures representing bits of knowledge. Like I would be talking of objects, concepts, facts, rules, strategies, and we could use different representations to show what we mean by these different things. For example, I could use a string like red to represent the color red, or I could use a string like car 1 to represent my car. And then if I write a very simple statement like red car 1, I would then be able to immediately see that this represents the fact that my car is red. Intelligent behavior thereafter can be achieved through manipulation of those symbol structures. Therefore, it's important for us to answer two questions. One, how do we represent this knowledge in form of structures, and how do we implement the process of reasoning? In order to understand this, let us first try to understand what we mean by representation. As I was telling you, I could use a string like red to mean the color red, or a string like car1 to mean that that's my car. So representation is a relationship between two domains. The first is meant to stand for or take the place of the second. In the example that I was illustrating, red is standing for the red color. Usually the first domain, the representer, is more concrete, immediate, or accessible in some way than the second. It's like you are driving on a highway and you see on a signpost a hamburger. Now immediately you would know that some fast food restaurant is nearby. So here is the hamburger representing the fast food restaurant. The type of representer that we will be most concerned with here would be formal symbols. So these are character or group of characters taken from some predetermined alphabet. Like for example, the digit 7 stands for the number 7, as does the group letters V11. Now what is knowledge representation then? To answer this question, what is knowledge representation? The best reference that we can think of is the paper by Davies, Schroep and his colleague on what is knowledge representation. According to them, a knowledge representation has the role of a surrogate. That is, I should look at the representation as a surrogate of what is being represented, and it would be a set of ontological commitments that I make. Now one needs to remember at this point that a knowledge representation is not a data structure. It is a set of ontological commitments about what is there that I am representing. The third role of knowledge representation is that of a fragmentary theory of intelligent reasoning. Now this brings us to the question of what is intelligent reasoning. Intelligent reasoning, I could take the logical view as well as the psychological view. But then here we keep ourselves restricted to the logical view, and we will look at which inferences are sanctioned, which inferences are recommended. The fourth role of knowledge representation is as a medium for efficient computation. And then they have listed the fifth and the final role of knowledge representation as a medium of human expression. We will look at each of them one by one in the next couple of slides. So let us look at what we mean by knowledge representation as a surrogate. When we say knowledge representation is a surrogate, we mean it is a substitute for the thing itself. So it is used to enable an entity to determine consequences by reasoning about the world. Next, it is a set of ontological commitments. That means having a knowledge representation, I am now able to answer a question like, in what terms should I think about the world? Now this is one important aspect that we need to understand, that ontology means the world as we see it. So in what terms should I think about the world? The knowledge representation gives me an answer to that question. As a fragmentary theory of intelligent reasoning, it could be expressed in three components. One, the representation's fundamental conception of intelligent reasoning. Two, the set of inferences the representation sanctions. And three, the set of inferences it recommends. Finally, knowledge representation is a medium for pragmatically efficient computation. That is, it provides a computational environment in which reasoning is accomplished. Now, one contribution to this pragmatic efficiency is supplied by the guidance a representation provides for organizing information. So a representation allows you to organize information in the most efficient way so as to be able to make the recommended inferences from it. It's a medium of human expression, that is, it is a form of language in which we see or say things about the world. So knowledge representation, as I have been emphasizing from the beginning, is an important sub-area of artificial intelligence, which is concerned with understanding, designing, implementing ways of representing information in computer so that programs or particularly intelligent agents can use this information. Now that information would be used to derive new information, to converse with people in natural languages, to decide what to do next, that is to take decisions, to plan future activities, and to solve problems in areas that normally require human expertise. Let us now focus on what we mean by reasoning. Now, having said that representation is about getting to some symbols, reasoning is the use of these symbolic representations of some statements in order to derive new ones from them. One must realize that statements are abstract objects. Their representations are the concrete objects that we have created and we can easily manipulate. Knowledge representation schemes would be useless without the ability to reason with them. And that is why we say knowledge representation and reasoning together. We do not only look at the representation part. Reasoning is an integral part of knowledge representation. And that is why the term is knowledge representation and reasoning. Now, how does knowledge representation and reasoning work? One realization that one needs to have even before you start working with knowledge representation and reasoning is that any form of intelligence requires knowledge, and computational models of intelligence requires models of knowledge on which to work on to get or infer new knowledge. Use formalisms to write down knowledge, and then these formalisms must be expressive enough to capture human knowledge. They must be precise enough to be understood by machines. So this is something that I would love to emphasize one more time, that when we are trying to use formalisms to write down the knowledge for a given problem, we would definitely want them to be expressive, so as we can capture as much human knowledge as possible. But then it needs to be precise as well to be understood by the machines. Separate knowledge from computational mechanisms that process it is very, very important. We need to understand that the knowledge and the computational mechanisms that process it need to be separated. And that is why I emphasized in the beginning that knowledge representation is not about having a data structure. So there is an important part of cognitive model in what the organism knows, but then we should not mix both the knowledge and the computational mechanism of a system when we are trying to create an intelligent system with a knowledge representation reasoning. So the next question arises is, how can knowledge be represented? Now in the very beginning, I had pointed out that there are two approaches to AI. One, the symbolic AI, which is about creating intelligence through manipulation of symbols. The other approach is the connectionist AI, which is about creating the computational model of the human brain. Depending on which approach you take, you could have symbolic methods of representing knowledge, which would involve things like declarative languages, imperative languages, hybrid languages like Prolog, rules, frames, semantic networks, so on and so forth. We could have non-symbolic methods of knowledge representation, the popular among them being neural networks and genetic algorithms. Now let us quickly focus on what we mean by knowledge representation languages. Now rather than general purpose languages like C++, Java, knowledge representation requires use of special purpose formalisms. A knowledge representation language should allow one to represent adequately the knowledge you need for the problem, two, do it in clear, precise and natural way, three, allow you to reason on that knowledge, drawing new conclusions. We will look at each of them one by one. So what are the requirements for a knowledge representation language? A knowledge representation language should have the following characteristics. One, it should have representational adequacy. It should be good enough to represent the problem that I am thinking of representing. So it must be expressive enough to cover all the ideas that needs to be represented. It must have clear syntax and semantics. How to write a particular proposition in that language and what is the meaning associated with that proposition, it needs to be very clear. Third, it must have what is called inferential adequacy. One needs to have the ability to derive new knowledge from the given set of statements in the knowledge representation. That is, one would love to infer, or what we say the KR language should have inferential adequacy. It must be that when I am deriving new knowledge from existing statements in the knowledge representation, it should do it efficiently, and that is what is called inferential efficiency. And finally, the knowledge representation that I have should have some naturalness, in the sense that a human being should be able to make out what is being represented by actually looking at it and trying to get the essence of the thing. We will come back to this when we will be talking of what we mean by a KR language being natural. Now, in practice, no one language is perfect, and different languages are suitable for different problems. Let us first try to understand what we mean by representational adequacy. Consider the following facts here. The first statement says, Mohan believes no one likes cricket. The second statement says, most children believe in Santa. And the third statement says, Mr. Kumar will have to finish his assignment before he can start working on his project. Now, I could have used a language like C and represent these statements as strings. Can I represent all these as strings? Maybe yes. But then the question is, if I want to manipulate and draw conclusions, I would have a lot of a problem. So, how do we represent things formally in a way that can be manipulated in a computer program? That is what is answered by the idea of representational adequacy. Some notations or languages only allow you to represent certain things. That is fine. But if it represents, it should be manipulable. Now, concepts like time, belief, uncertainty, all are hard to represent. In fact, in this course, we will look at how to represent uncertainty, and also we will talk of how to represent beliefs and time and some point of our discussion. A representation need to have well-defined syntax and semantics. So, knowledge representation languages should have precise syntax and semantics. One must know exactly what an expression means in terms of objects in the real world. This is because one needs to understand that when I am doing knowledge representation and reasoning, I am actually mapping the real world to representation of facts in the computer, and then this is where inferences are being drawn and new conclusions are being gathered. Now, after the new conclusions are being gathered, it is important that I can map back to the real world. If I do not have clear semantics on what is the meaning of each of the symbols that I am using here, this mapping back to the real world will be either ambiguous or would not be possible at all. So, one needs to have precise syntax and semantics for a knowledge representation language. This is something that one needs to understand very, very clearly. This is precisely because I bring from the real world into the computer the facts of the world in terms of a representation that I myself define and use. And that representation must therefore have precise meaning associated to it, every symbol that I am using. So, we should exactly know what an expression means in terms of objects in the real world. Now, we will take a moment to understand what we mean by syntax of a KR language. In any knowledge representation, there would be a group of symbols arranged in some way. But then, what would be considered properly formed and what would not be considered properly formed is defined by the syntax of that knowledge representation language. So, in English, for example, if I take two strings now, the first string, the cat my mother loves, actually is a well formed phrase. Whereas, if you take the next one, the my loves mother cat is not a well formed phrase, and therefore, the first passes the syntax of English, the second does not. The syntax consists of a set of symbols used by the language and a set of rules according to which the symbol can be combined to form proper sentences. So, we need to understand that for a knowledge representation language, we must have a precise syntax defined. The semantics, on the other hand, specifies what the well-formed expressions of a knowledge representation language are supposed to mean. The semantics actually is a mapping between the symbols, combination of symbols, proposition of languages, and concepts of the world to which they refer. So, a proposition in a knowledge representation language does not mean anything on its own. The semantics, that is the meaning of the proposition, must be defined by the language author through something called the interpretation. So, that is very important, that I have a precise syntax and a precise semantics. Now, let us focus on the next requirement of a knowledge representation language, which is inferential adequacy. Representing knowledge would be really not interesting unless you can use it to make inferences. We should be able to draw new conclusion from existing facts. If I say a statement like, if it's raining, John never goes out, and I say it's raining today, then one can immediately draw a conclusion that John is not going to go out today. The ability to derive this new information that John is not going out today based on two bits of information that I have specified. One, if it's raining, John never goes out. Two, it's raining today. That ability that I can get a new inference drawn is called inferential adequacy. So, we should come up with solutions to complex problem using the represented knowledge, and that can only happen if the knowledge has enough inferential adequacy. Inferential adequacy in a sense refers to how easy it is to draw inferences using the represented knowledge. Representing everything as natural language strings would really have good representational adequacy and naturalness, but very poor inferential adequacy. Now, let us take a minute to understand what we mean by this. This is because natural language strings, if I use to represent a certain problem, I can represent anything and everything using natural language strings. But given a group of natural language strings, it would be very difficult for a computational mechanism to draw a new group of natural language strings. Now, this is something we must take note, that this is not that this is impossible, but then we are talking of the level of difficulty. The difficulty on working with just natural language strings would be far more than the difficulty of working with a group of symbols that I would use to refer to those natural language strings. And therefore, if I am doing something in natural language strings, I would have very good representational adequacy, but I would have very poor inferential adequacy. Next requirement is about inferential efficiency. I should be able to make, in principle, complex deductions given the knowledge represented in a sophisticated language. Now, the more complex the possible deductions are, the less efficient will be the reasoner. But then I must have the ability to make complex deductions. So, we need representation and inference systems which are sufficient for the task without being hopelessly inefficient. Let us now look back on what we had introduced in one of the characteristics of a KR language, that is the naturalness. If our representation schema is quite intuitive and natural for the human reader, it would help both the representation and the reasoning. So, could represent the fact that my car is red using the notation something like X, Y, Z, Z, Y, bang, zing, where X, Y, Z, Z, Y could refer to redness, zing refers to my car, and bang here is used in some way to assign properties. But then for a human reader, the statement here would really be not comprehensible. Contrast this with the following. Let us write something like car SMH and color red, where car X can refer to the owner X and color X can refer to the X color. Now, the second group of statements that I have written is more understandable or natural in some way than the first one. A knowledge representation language needs to be something along the second line than along the first, which is very incomprehensible. The desired features of a knowledge representation language, therefore, would be at the epistemological level, we need to have clarity and expressiveness. At the logical level, one needs to have elegant syntax and semantics. It needs to be decidable or tractable. It needs to be sound and complete in terms of its inference. And in terms of implementation, we need to have space and time efficiency, and it must be extensible. This is where we would see that for knowledge representation and reasoning, formal logic is the first choice. Why is logic the first choice for a knowledge representation language? Is precisely for the reason that logic is a formal language with precisely defined syntax and semantics, and it supports sound inference. The language is independent of domain of application. Now, there exists different logics which allows one to represent different kinds of things with more or less efficient inference. Like we have propositional logic, predicate logic, temporal logic, modal logic, description logic, so on and so forth. Representing some things in logic may not be very natural, but then inferences would be very good. At times inferences may not be efficient as well. Under such circumstances, more specialized languages may be better. But here in this course, we will focus on formal logic for knowledge representation and reasoning. So what are the advantages of logic for knowledge representation? Like all declarative languages, logic is compact, task independent, modular, reusable, flexible, and maintainable. Logic has formal, well-defined semantics, and logic is expressive. Historically, logic is the first knowledge representation language. First order logic has been the knowledge representation language for artificial intelligence from around late 50s. Around 65, we had seen Robinson come up with resolution, which meant real hope for universally applicable proof method. We will look at resolution as part of our discussion on first order logic. Around 70s, a number of rivals to logic emerged, like semantic networks, rules, frames. However, they had unclear semantics and inference, and around 75 with logic programming, we did decrease expressivity, but there was a huge increase in efficiency. Logic regained its place in AI as a knowledge representation language. Around 1980s, there was non-monotonic reasoning introduced, which could deal with common sense knowledge. So as part of introduction to knowledge representation and reasoning, we'll start with propositional logic. We'll see propositional logic has drawbacks. So we will consider the more general first order predicate calculus. Now first order logic or first order predicate calculus is symbolized reasoning, in which each sentence is broken into a subject, and a predicate. The predicate modifies or defines the properties of the subject. First order logic provides a well-defined language for us to express knowledge, and this is what we will take up for discussion in our next class. Thank you.